Yeah, that looks great, Bard.
Yeah, that's it. Okay, welcome everyone. I am Robin Burgess, and with Kelsey Jack, we've set up this PhD course on environmental economics with the two organizations, BRED and the International Growth Center. So we're very pleased today to have Bård Harstad from Stanford talking about international climate action. And I think what's interesting about Bård's work is that the fundamental problem with climate change is that the stuff that creates climate change has effects well beyond national borders. So it extends well beyond political jurisdictions, which means that you need some degree of international policy to confront it, because the benefits from development are enjoyed by the country or the place where those things are happening, but the externalities from that extend everywhere. So I think Bård has really been the pioneer in that area of work. He comes more from economic theory, so he's worked a lot on treaties, on contracts and so on. But I think what's really, really original here, which we'll be hearing about today, is this sort of push into thinking about how we get some international climate action. So without further ado, I'm going to pass it over to Bård to take it away. Thank you. One final thing before I do that is, if you would like to be a live volunteer, which would mean that you could raise your hand and ask questions, could you raise your hand now in the on Zoom, and then Caleb can promote you up to being a live participant. And if you do that, could you keep your video on so we have some semblance of an audience and Bård isn't talking into a black box? Okay, thank you very much. And there'll be a quarter of an hour to 20 minutes at the end for people to ask any questions. Okay, thanks a lot, Bård.
Thank you, Robin. It's great to see you from so many different places. For me, it's early morning, but and that's a great way to start a day. No, I think Robin is not correct in that I have been a pioneer in this field, but I have been a very enthusiastic student of the earlier work on this field, and I think it's a very important work to continue to work on also for us. So what I will do is that I will try to cover quite a lot of ground in this 1 hour that I have. I will talk about bargaining, different bargaining games, but not very much, so that doesn't count like a point. But I will talk about dynamic climate change games between countries, because I think that the externality between countries is extremely important to take into account. Then I will talk about the incentive to participate instead of free riding in that international agreement, and also an incentive to comply instead of defection after you have signed an agreement. Those incentives will vary depending on the institutional design, which I will get back to in the end. And the motivation for this, which was actually based, so much of the work here was based on some teaching needs that I had to do, and I wanted to say something about the difference between the Kyoto Agreement from 1997 and the Paris Agreement from 2015. And I felt that we didn't really have the right framework to compare those agreements. So that is what this lecture notes, and this lecture will focus quite a lot on. So let's start with the Kyoto Protocol. We had then many countries signing the agreement, but in the end it was only 37 countries who were committed to kind of reduce emissions. The emission cuts were about 5% on average compared to how much these countries have emitted in 1990. But that was an average number, and the countries bargained about exceptions and how much individual countries should cut. These cuts were so-called legally binding. It meant that one could hold countries accountable to the emission cuts that they had pledged or promised. But of course, there is no world government. But in the US, for example, this has some bite nevertheless, because that means that the states can hold the federal government accountable if the federal government has signed an international law, because that then in turn becomes a national law. I will get back to this later. The commitment period means that it means the number of years over which the emission cut that you promised to do will be valid. After this 5-year commitment period, you will start, the idea is that you will start one more time with another commitment period. And so you will do this repeatedly, depending on, for example, how much technology has developed in the meanwhile. But these technology investments, they are not part of the agreement themselves. They have been decided, have always been decided on non-cooperatively by individual countries, even though they have been recognized as being very important. So the bargaining procedure in the Kyoto Protocol is extremely hard to describe because it's very messy, but sometimes it has been referred to as a top-down negotiations, in the sense that, just like with the international trade negotiations, countries are comparing their offers and contributions, and they may refer to another contributions, and they can even make conditional offers, so that I can say, if I'm a country, I can say that I will cut this much, but if other countries are making larger cuts, I can also deepen my cut. So this conditionality, of course, is very important in bargaining theory, as we know in economics. But the 2015 agreement was quite different. So now this is the New York Times trying to describe the Kyoto Protocol. Instead of pursuing this top-down agreement, as in Paris, the organizers have asked every country to submit a national plan that lays out by how much they plan to reduce emissions in the years ahead. So the agreement itself states that each party, which is a country, shall prepare and maintain a nationally determined contributions on what it intends to achieve. So it's decided on by the countries themselves. So as David Victor, he has been advising this change to the pledge and review procedure in Paris. He states that instead of setting commitments through centralized bargaining, as in Kyoto, the Paris approach sets the countries free to make their own. So the Paris talks is a bit like a potluck dinner, where guests bring what they can to the table. And when you think about it might be worrying that you don't have this conditionality aspect, as I mentioned, that there is in typical top-down bargaining procedures. So political scientists have also been worried about this, and they are worried that many governments will be tempted to use this vagueness and the discretion to limit the scope of their actions. And economists like Christian Gollier and John Tirole have, partly for these reasons, said that the pledge and review strategy in Paris is completely inadequate. So that is one difference between Kyoto and Paris. The fact that there is not, you don't see so much of this conditionality. But there are many other differences. The claim to success for Paris Agreement is that now almost basically every country in the world is participating, in contrast to Kyoto. The emission cuts are not legally binding, however. And a fourth difference between the two agreements is that, and that's interesting by itself, I think, because it means that one design was chosen by the world community in the 1990s, and 20 years later, the world community went for and decided on to use a different bargaining procedure, this pledge and review. And this, despite all these four differences, the treaties are, to some extent, similar in other respects. For example, this commitment period that I mentioned is going to be 5 years, also for the Paris Agreement. So basically, this is going to be the outline of this lecture. I will start to talk a little bit about the difference in bargaining game, and then I will talk about participation, legally bindingness, and the choice of procedure, and even the commitment time period, if you have time. Okay, I will not say that much about the bargaining games, but you might know already the Nash bargaining solution, which would, in our context, say that if GI is country I's greenhouse gas emission level, and then a country like country J will get a utility or a continuation value utility, if you take into account that this is a long-lasting game, which depends on its own country's emission of greenhouse gases, but also the vector of other countries' greenhouse gas emissions. So if you have such a utility, then the Nash bargaining solution suggests that each GI should maximize the product of all these utilities if they are compared to the business as usual utilities or the outside of options. And that's a very neat and basically easy, simple formula to use. And it's very popular to use in applications in economics, including environmental economics and climate change economics. We also have an axiomatization for this particular solution, which is provided by John Nash himself, and also non-cooperative game, like the Nash-Damal game, where he described a particular game which would implement that as the bargaining solution. And since that time, we have also seen alternating bargaining offer games, basically like those of Rubinstein, which can also implement the Nash bargaining solution. So there's strong reasons to believe that this is not a crazy bargaining outcome to use in economics. But the worry is that when we describe this bargaining procedure in the Paris and how it differed from that of Kyoto, one may think that this approximation is no longer justifiable for the Paris Agreement, because in contrast to Rubinstein's bargaining game, it is now no longer the case that when I make an offer, I can describe an entire vector of emission levels. Maybe that was not the case in Kyoto either, but there was some kind of conditionality which is lacking for the pledge and the review procedure, which is used in the Paris Agreement. When I'm just coming up with my number myself, then it might be tempting for me to place a higher weight on my own utility and a lower weight on the other country's utilities. One easy way of capturing this intuition is to assume that now I will set a GI in my country, which is maximizing an asymmetric Nash product, where I take into account my utility compared to the default option of no agreement. And also the utility of the other countries, but the weight I place on other countries relative to myself might be 1, as with the Nash bargaining solution, but it might also be less than 1 if you have a weaker bargaining game in place. So what I will not basically describe what this W is, this weight which I place on other countries' utility. I will take it as a parameter in the model. But there are ways of endogenizing it. For example, if you have uncertainty, if I'm uncertain about how much you are going to accept, then I will maybe be worried that if I don't put a place an emission cut which is sufficiently attractive on the table, maybe you will not accept because for some reason. That can motivate me to try to make the emission cut sufficiently attractive to you. The more uncertainty, the more might the weight be on your utility compared to my own utility when I make my offer. So this is just it's possible to discuss this in more detail. And in an article in Journal of Economic Theory this year, I describe how, and I try to give a better micro foundation for why this could maybe make sense for the pledge and review procedure used in Paris. But I will not do that now. I will just take now the W as a parameter, and I will postulate that weight on other countries' utilities might be smaller when we are using the pledge and review procedure used in Paris Agreement than if we are having this top-down approach, which was maybe a better characterization of the Kyoto Protocol. And then we will here today analyze the consequence of the different bargaining games. So just to give you a very simple example, suppose that I have a utility or continuation value utility, which it depends on 2 things. It depends on all your emission cuts or all your contributions, and the sum of contributions give me some benefit alpha. But the cost of making a contribution myself, in terms of that is a cost which increases in my own contribution, and suppose that cost is quadratic. Okay, so if I in the non-cooperative game, if I don't place no utility on you, I will contribute nothing, because my utility only depends on your contributions. But if I place a weight W on your utilities, you can check that in that case I will contribute a little bit. I will contribute an amount which is proportional to the weight I place on your utility, which can depend on this bargaining game. It will also be proportional to the number of other countries, which I will internalize some of the utility of. And the weight and the value they place on my contributions divided by basically my cost. So that's intuitive. Just an example to keep in mind. So now I will proceed by talking about dynamic climate change games, and I will talk about participation and compliance and institutional design. The most, some of these parts can be understood without necessarily referring to the other parts. So if you are lost on some of the slides, you will be able to catch up when I move on to the next point. Maybe this part is the most technical one, but I will try to focus on intuition, and I will not go that much into the details. But I will start by going back to the Paris Agreement, which also states that each country shall communicate a contribution every 5 years. And the idea of doing this repeatedly every 5 years is probably that this time frame will give countries an opportunity to capture technological progress. So that if we have been able to have so much progress on technology, that based on that technology, we can make deeper cuts in the future, then this 5-year period allows us to update and do better over time. And there can be a trade-off. You don't want this updating to be too short, and I will get back to that later. So 5 years is the chosen number. Of course, one may be worried that maybe the countries will not have incentives to develop new technologies if that is not a part of the agreement itself, especially if the weight I place on the other countries' utilities in the bargaining game is relatively small. So to try to understand this, consider the following model or utility function. I will assume that my utility is linear in all emissions, and so my utility at some point in time is decreasing in the sum of greenhouse gas emissions, multiplied with a parameter A. This doesn't necessarily mean that we have a flow environmental problem, so that once we emit, it harms me right now, but never again in the future. Because it could well be that when we emit a unit of carbon dioxide, it can stay in the atmosphere for a long time before it gradually decays. However, if we simplify by thinking that the cost of for a country of a larger stock of carbon dioxide in the atmosphere is more or less linear in that stock, then I know that if one of you emit 1 unit of stock in the atmosphere, the cost of that unit, even if it stays for a long time, can be calculated at the present discounted cost of a unit of, or maybe a ton of carbon dioxide, which will be independent of the stock itself, because if the cost is linear, the marginal cost is going to be constant. And that present discounted value can be defined as this little a. So it could be that I here take into account that the unit of emissions are staying in the atmosphere for a long time, but I account for it already now. And I simplify by calling that cost simply A. So why do I do it? Why do I emit? Because it gives me benefit, or alternatively, it gives me this utility if I do not emit. If I do not emit, I cannot consume so much energy, and that will give me this utility. That is the second term in this utility function. Here I assume that there is a bliss point, BIT, which is exogenous, and I would like, if I could, if there was no cost, to consume so much energy. The energy can come from 2 sources, the fossil fuels, or alternatively, the stock of renewable energy, which is also producing energy. For consumption purposes, I assume that I don't care what is the source. But if the sum of these sources is far away from my bliss point, I get this utility, which is quadratic in a difference, like in this term. So it's better to consume energy from the renewables because it does not lead to climate change damages. But it's costly. If I want to increase my stock of renewable energy, I must invest little RT, and that is a cost. And just for simplification, it is assumed here that that cost is a quadratic. So based on this very simple linear quadratic utility function, we can calculate what is the equilibrium if there is no cooperation at all. Then we can consider the so-called business as usual or mark of perfect equilibrium, which will be the following. Suppose that my decision on G and R are made sequentially. So first I invest and then I pollute, for example. Then my pollution level will be a function of how much energy I have. The more energy or windmills, for example, I have, the less I need to pollute in order to be close to my bliss point B. I take this into account when I invest, and the fact that the more I invest in windmills, the less I need to pollute. Therefore, if the cost of pollution, A, is very large, I will find it optimal to invest more in renewable energy. So that is a very simple benchmark. So compared to this benchmark, the world community has an incentive to do better, because here I don't take any of the externalities into account. To capture how much better we can do, let me define Xi as the contribution. That is basically the emission cut, which I promise if I pollute GIT, compared to this business as usual level up here. So if Xi is 0, I make no contribution because I will pollute the same as I would have done in the absence of any agreement. But if GI is, which is what I will promise to pollute, is much smaller than the business as usual level, then I make a contribution, and that is what I call Xi. Suppose now that I do this for T periods, which is maybe 5 years, before we can play this game again. Basically, then we can divide the problem in two. First, what is X? Second, given X, how much should I invest in technology? Basically, these small r's. So given X, if you think about the problem first without the X, I basically have an optimal control theory problem. I have a vector of X's, one for myself and the other are from the other countries. And I have to now think about how much to invest in the next 5 years in renewable energy. That is an optimal control theory problem. And for our purposes, we might be especially interested in what this agreement will achieve compared to the business as usual level. So what I will now define is, so X is how much I cut pollution with, and similarly, I will define Y as how much I increase investment in because of this agreement. So Y is increasing R in R compared to the business as usual level. And because this is a simple control theory problem, I can calculate what is this additional investment Y. And I will not go through all the steps. I will just show you the formula. It looks messy, but in fact, it's not so. It's quite simple, because what this says is that the additional investment, that is the increase in R, investment in alternative energy, compared to the business as usual, that is proportional to my contribution Xi. It's linear in the contribution Xi, where Xi, remember, was the emission cut that I promised to make compared to some of the business as usual level. So if I make no emission cut compared to the business as usual level, I will make no additional investment compared to the business as usual level. But if the emission cut is large, I will invest more. And based on this, we can also calculate the accumulation of investments because of this agreement. And that accumulation, that means not only the investment I make at time 1, but also time 2 and time 3 and so on. And that is also going to be proportional to X. And that is the simplification, which is neat, but it also depends on the other parameters in a relatively ugly way. But that is not something we need to focus on today. So when I know that Y, my equilibrium investment, basically, is proportional to X, and I also know that all your investments in renewable energy is going to be proportional to your emission cut, then I can plug those equilibrium investments into the utility functions, and I can calculate what my utility function, or basically my continuation value, will be from the time as soon as we have agreed on the X's. As soon as we have agreed on the X's, I know that thereafter your emission cuts will be given by this X, and your investment will be a function of that X in this way. I can plug that into utility function. I can calculate what my continuation value will be from that point on, out as soon as we have agreed on x's. And because my utility function was, for simplicity, was assumed to be linear quadratic, and this y is linear in x, everything will be linear quadratic in x. So I can write it in this form. My continuation value will depend on the vector of x's, but it's going to be linear quadratic. These parameters are going to be not neat, but that doesn't really matter, because as long as this linear quadratic in x, in fact, this looks exactly like this example E that I referred to earlier. Remember? And when my utility function is in this simple way, then when I mentioned example E after I talked about the bargaining game, I also say that for that particular example, the bargaining game, as a pledge and jury bargaining game, will lead to a contribution which is proportional to the weight I place on other utilities in a bargaining game, multiplied with the number of them, multiplied with the benefit they get, divided by my cost of contributing. That's what I said. For the Nash bargaining solution, the W is 1, but for pledge and review, it's likely that the W is smaller than 1 because we don't have this conditionality built in to the bargaining game. But this is great, because when I know that X is basically proportional to W in this way, then we can plug also those equilibrium X's into the utility function up here, which can be written in this way. And then we get that the continuation value will be a function of the W. And it's going to be maximized when the W is 1. So the Nash bargaining solution is giving the best solution, because that is a situation where in the bargaining game, I place the same weight on your utility as put on my own utility. And everyone is doing that. That leads to the best outcome. That leads to the best outcome in the sense that there is no, in this world, where we, for simplicity, assume that countries are similar. Maybe they have different bliss points and energy, but otherwise they are quite similar. In this world, then the utility, the equal utility we all get from the bargaining game, is maximized if W is equal to 1. That means that we put the same weight on each other's utility. If the W is less than 1, we get a lower continuation value utility, because a smaller W will reduce the contributions, the emission cuts, the excess, and because of that, it will also reduce the investments in alternative energy. And ultimately, it will lead to a lower welfare. And this is basically, I didn't talk about after this, we are playing a game again after T periods, but this is all taken into account. So we have to take that into account. But this result is quite intuitive. And this also is maybe the intuition behind the criticism of the pledge and review procedure. If you have a lower weight on others' utility, because I don't need to take their utilities into account when we don't have this conditionality built in, then you don't get the same emission cuts as you would have gotten with the Nash bargaining solution. And we get lower investments. Okay. That's so far negative news for the Paris Agreement. Yeah. Let me now move on to talk about participation, because so far I just assumed that all countries were bargaining. I just assumed it for exogenous reasons. We should not simply assume that. We have to think about what are the incentives really for the countries to bargain if they don't have to bargain, if they can just stay home and free ride on the contributions of other countries. So there are many ways of trying to formalize the participation decision or the coalition formation decision. There are many ways of doing it. I will not give you a survey of all the different ways. I will pick maybe the most standard way, just off the shelf. A very simple way of doing this, which is based basically on the IO literature from the 80s, where they also studied how different firms wanted to bargain or to be in a collusion or not. If you are in a collusion, you can make a cooperative agreement with the other firms to raise the price. But if you're out, you can also enjoy the higher price, so you can free ride. And that particular model has been adopted in many different applications, including environmental economics. It's very simple. Consider the following. An upper bar is the largest number of participants, the number of countries in the world. And every one of them at the same time decide whether to be in or out. Those who are in, that's the participants. They are, we will assume that they are going to play the game that we just described. When they are bargaining over the X's and then they invest and so on for T periods. And after that, they will do it for another T periods. But those who are out, those who are free riding, they can do whatever they want. They are free, okay? And based on the model we have above, they will find it optimal to emit the business as usual levels and invest just as a business as usual level, no matter what the coalition will do. The reason why they will do that, no matter what the coalition will do, is because it's thanks to the simplifying assumption that we made, which was that the cost of all these greenhouse gas emissions is linear. So the marginal cost for me, if I emit more, is not depending on how much you emit. Therefore, the problem are kind of separable, and I will find it optimal if I'm a free riding country to basically set X equal to 0. Because remember, X was the emission cuts relative to the business as usual level. So that's simple. That's what I will do if I'm free riding. The problem is that if I free ride, there will be one less member in the coalition than if I participated. And I also know from what we have discussed before, that if therefore I free ride, the rest of the coalition members will contribute less, because they will internalize the externality of one fewer member. If I instead participated, they would find it optimal to contribute more. So that is my trade-off. I can free ride, sure, but then I will not be able to motivate the other countries to deepen their emission cuts. That is the trade-off. And I know how much impact my participation will have on the other countries' emission cuts, because we had a formula for that. That was that X was proportional to N minus 1, where N was the number of coalition members. So if that drops, X drops. And because the utility function, and in fact the continuation value utility function, is so simple, it's linear quadratic, I can easily plug in and in order to find what X is for the coalition members, if I'm in or out. It's just that N will be reduced by 1 unit. And if I'm in, I will also be taking your externalities into account. So then I will, to some extent, depending on the weight W, and then I can also calculate what are the utility if I'm in or out. It's all linear quadratic. It's just a little simple, a few steps with the linear algebra. And then I can find out that whether or not I will be in will basically depend on how many others are going to participate. Because if the coalition is expected to be very large, then it's very costly for me to be participating. Because if I'm in, I will take a certain fraction W of your utility into account for a large number of parties. That is very costly. And it's especially costly because because in this utility function that we know that the cost of contribution is convex in my contribution. And if my contribution increases in the coalition size, my cost of participating will also increase in a quadratic way in the coalition size. So at some point, the coalition is so big that I rather free ride. If the coalition is smaller, it's okay, I can participate, it's not so costly. So that is giving me a trade-off, and it's giving me an equilibrium N star. That is the largest coalition that can be sustained given this simple game. So a typical result here is that the number is 3. Basically, if you plug in W equal to 1, because you're assuming, and suppose that we are assuming that we're using the Nash bargaining solution, then you can do this algebra to see whether I'm better to be in or out, and it depends on the collision size. And if the collision size is more than 3, then I prefer to be out and free ride. Okay, it's a bit odd, perhaps, that it depends on a particular number instead of the parameters of the model. But the reason is that, for example, the cost of climate change, A, that is going to be canceling it out, because the bigger is A, the more important it is that I can motivate other countries to contribute. So that should lead you to think that it's more important for me to be in if A, the cost of climate change is large. But if A is large, it will also be the case that I will be expected to contribute more. So the cost of participating is also increasing in A. So the effect of that parameter will cancel out when I consider whether the benefit is larger than the cost of participation. That's why it ends up with a particular number. But it's a very small number. It almost doesn't make any sense when we look on how big minor collisions are in the world. So a lot of research have been trying to study why or when the collision can be bigger than 3. And there are Finis and Mouse, for example, they say that if this weight, for some reason, and I don't really explain why, if that reason is less than 1, maybe the collision can be bigger. And that is basically the reason why the collision can be bigger in this simple model that we have discussed so far. Because if W is less than 1, then you can use the same simple algebra, which I skipped, to show that the collision size is basically 1 plus 2 divided by W, which is equal to 3 if W is 1. But if W is less than 1, this is a number which is bigger than 3. Okay? Why is it bigger than 3? Because if the W is small, what does it mean? It means that if I'm in, I will contribute more than if I'm out, because I will take a fraction W of your utilities into account. If this fraction W is small, the cost of being in is not that great. And it's not a big cost for me to be in. To some extent, you may say that, well, it's not a big benefit either. Because if everyone is just taking a fraction W of my into account, and this fraction is small, the benefit of participating is not that great. So both the benefit and the cost are going to be smaller if W is small. But because the cost of contribution turns out to be convex, the cost effect dominates. So that if W is small, it's more likely that I will find optimal to be in instead of out of this coalition. And that is why I'm willing to participate even if N is large. So the smaller is the W, the weight I will basically put on you in equilibrium in a bargaining game, the bigger is the collision that you can sustain. One intuition for this is, think about this extreme case where W is 0. Well, of course, then I can participate because there is no cost for me to participate. I will, in any case, just do what I want to do. So then you can have as large collision as you want. So when W goes to 0, this number goes to infinity. But this simple logic implies that now we can see that there is a benefit of pledge and review if pledge and review means that W is smaller. The benefit is that you can attract a bigger coalition. You can get a bigger coalition. And this simple result, which we now got when we endogenize the collision size in a very simple way, implied that this proposition 1 is now reversed. Now it will be the case that a smaller W will increase aggregate contributions, and because of the collision size will increase. And because aggregate contributions, basically emission cuts, will increase, investments will also increase, and we are all better off. So in this case, we are better off with a smaller W. So that is why proposition 1 was reversed. So you might think that now we will use the Paris Agreement in a better way, because we can see that now one advantage of this simpler or less mandatory or conditionality bargaining game is that you can attract a bigger coalition. So then that brings me basically to the second point here, is that with this difference bargaining game, we can also see that that has the potential of explaining why the coalition size is much bigger in the Paris Agreement. Okay, so based on this, we have now concluded that the Paris Agreement is best. But that is a bit simple, because we have not taken realistic constraints into account. Let me go straight to a figure. So please start by looking only on the top figure here. Here, this is the number of countries in equilibrium as a function of W, where W is depending on the bargaining game. With pledge review, it's smaller. With Nash bargaining solution, it is equal to 1. We found this formula, although we must take into account that the number of countries must be a natural number, and it cannot be 3.5, for example. But abstracting from that, it will be a number going like that. That figure, only that line, will imply that when we plug this number and also the contributions into the utility function, we get that each country will have each participating country will have a continuation value, which is decreasing in W. If W is small, N increases, and that's why the continuation value increases. So that is the reasons why I say that now the result is reversed. With a smaller W, leads us to a bigger coalition and a higher welfare. So the Paris Agreement is better. However, the reason why I draw this N upper bar and a bar is that there might be natural constraints on the coalition size. One constraint is obvious. There is a fixed number of countries in the world. We cannot trick more than that countries into participating. So if W is so small that eventually the equilibrium N reaches the number of countries in the world, then if W is even smaller than that, that has no additional benefit. It will not lead to a bigger coalition. So the only effect it will have is that the coalition will stay the same, but a small W will lead to lower emission cuts. And therefore also lower investment levels in alternative energy. And these lower emission cuts and lower investments means that the utility is also smaller. So that is why basically this continuation value will be non-monotonic in W. If W is so small that all the countries are participating anyway, then if it happens that W is even smaller than that, that is not beneficial. So that's one thing. Another constraint could be that it could come from the fact that we have not yet really considered heterogeneous countries. We could allow for some heterogeneous split point, but the model simplifies a lot if you assume that the countries are quite similar, which is of course not realistic. It's not realistic for many reasons, and one of the reasons is that if W is really small, say close to 1, it's not the case that in the world only 3 countries will participate. Think about Europe. Europe is, for example, a particularly supporting set of countries who are likely to be contributing no matter what. Not only because they have been pushing their climate change agenda for several years, but also because they already have the European Union, they already have an international agreement between one another. It's not that simple for a particular individual country to opt out from, say, the Paris Agreement. So that means that there might be a set of countries who is going to participate no matter what. We can call them committed countries. They may or may not be. But if N and the bar is that number of committed countries, then it will be the case that if W is so large that only those countries participate, then a larger W will not necessarily be bad. Because if the committed countries will participate no matter what, then a large W will mean that these participating countries, they will contribute more. So then a bigger W will increase the utilities. So now it's not so clear anymore what the best bargaining game will be if two different bargaining games have different Ws. But here is the intuition that we are trying to achieve. Suppose that you have a large number of countries in the world, and that is measured on this axis here. And very few of them are committed in the sense that they will participate no matter what. Then we know that a smaller W is better because it will motivate a larger coalition. That is this proposition 2 that I emphasized above. A bigger coalition is important, and that can be achieved if you have a pledge and a review bargaining game instead of a top-down Nash bargaining solution. But if you have few countries in the world, so that they're all participating anyway when W is small, or you have some countries are committed to participate, in the sense that they're all participating even if you have a large W, then it's not so clear. And then you can be in an area where actually it's better to have a bigger W, because the coalition size is not going to be that small when you have some committed countries. And that can be better than have a smaller W, because the coalition is then not likely to be that big, given the constraints on the number of countries in the world. What we may argue is that over time, the last 20 years, or between the 1990s and the 2010s, we might have moved in this direction up here. For two reasons. We might have moved up because what does risk n upper bar really measure? It measures the number of countries in the world, but more importantly, it should measure the number of important countries or the important climate emitters in the world. So if you want to have a model where all countries are similar, it's rather be a model of the countries which are similar or which are important in the climate change game. In the 1990s, there were many countries that were developing countries, and since that, some of them have become emerging economies, and they have become more important players in the climate change game internationally. So one can argue that the number of relevant players has increased since the 1990s to the 2010s. And that was one of the reasons why the US, for example, insisted that they have to move to a different system, which could motivate also Asia and in particular China to participate in agreement. So with a larger number of important players, we can see that it's now more important to move to a system which can motivate a larger coalition. And the pledge and review procedure can help with that. We might also argue that we have moved to the left. It's not necessarily the case that we need to do that, because as long as you have moved up, that's enough to explain why you might have moved from a situation where the top-down bargaining procedure was optimal to a situation where the pledge and review procedure was optimal. But it's also true that many of those countries who were participating in the Kyoto Protocol, and you can maybe consider them as the committed countries, some of them have since that time claimed that they would not participate in the Kyoto Protocol's second period. They rather preferred a global system, which mandated all countries to contribute. So the one interpretation of this is that the number of committed countries is not so large anymore. Either of these changes can be sufficient to rationalize the change to pledge and review. So that change might also be possible to explain. Now, I skipped this thing about compliance. So let me go back to that in the last few minutes. And that's a very important thing, because so far we have just assumed that if a country pledges X, it basically commits to X for a T periods. But we have to take into account that, well, it must be in the self-interest of this country to stick with that X instead of defecting to do what it wants. Because after all, there is no world government who can force the countries to comply to such a pledge. So it's not easy to deal with these compliance issues, because we then have to think about, okay, suppose a country promises a particular cut and later it decides to do something else. Then we have to think about what is the consequence of doing something else, which we call defection, because they're not complying. And this consequence is very unclear. It's very unclear what will happen to its neighbors and their willingness to cooperate in the future if a particular country defects. And one easy way of trying to study the limits of this force, the force that if I stop to cooperate, I could be worried that you will also stop to cooperate, at least for some time. And that cost can maybe motivate me to keep on complying. One way of studying the limit of this force, is to assume that if I stop to cooperate, you will all stop to cooperate forever. That is these trigger strategies, which is unrealistic, but it allows us to study the limit of this particular force. So and it's a simple way of doing it. So basically, it's then we have to calculate what is my utility in the, we already know the continuation value. We have already talked about that. But now I have to think about, suppose that you are complying to your axis, or the other participants in the coalition are complying to their axis, and I'm free to set whatever x I want, which means basically that I will set x equal to 0. I will do just as in the business as usual case. So then I get a bigger benefit because I can consume a bigger amount of energy in my country. But later, maybe the next period already, you will all set x equal to 0. It's easy to plug those zeros into my utility function to study when is it better for me to free ride one period, if later the next period we are all going back to the business as usual. So we know from other games that this will depend on the discount factor. If I think a lot about the future, in the sense that my discount factor, delta, is large, then I will not defect. It's too costly. But it will not only depend on the discount factor, it will also depend on this parameter in the bargaining game, W, okay? And that is what I want to emphasize here. If W is small, then it's not very costly for me to participate, right? We can actually consider two different cases with fixed, with the endogenous N and with fixed N. But for both settings, it's going to be true that if W is small, it's not that costly for me to participate, because the W measures how the fraction of your utility that I will internalize when I set my axis. If that fraction, this weight is small, I can just as well participate. The temptation to defect is much larger if W is large, as in a Nash bargaining solution, because then I will be expected to do a bigger emission cuts. So it will depend on this bargaining game. So it's possible that this condition could hold when W is small, but not when W is large. And if it does not hold, then we have a problem, because that means that the equilibrium emission cuts that we can hope for are going to be so large that countries are tempted to defect. And if that is true, we must find another way of motivating countries to participate. And the world community has thought about that. And that is maybe one interpretation of why they talk about emission cuts as being legally binding. That even though there is no world government, the fact that certain things are legally binding signals a greater seriousness by states, which will increase the political cost of violation. And that is maybe one way of trying to make the agreement credible, even if in isolation this compliance constraint would not hold. So then it's possible that this making the agreement like legally binding in this way might be necessary when a W is large, as with the Nash bargaining solution, even though it might not necessarily be required if the W is small, as with the pledge and review, because then the incentives to defect is smaller. This comparison has the potential to rationalize why the emission cuts under the top-down procedure was legally binding, but they're not legally binding with the pledge and the review procedure. Because it's more, in that case, it's more likely that they will be self-enforcing. Okay, so it seems like we can, based on this bargaining game, we can also think about how that will influence the coalition size, the incentives to comply, and the necessity to make the emission cuts legal binding, and also why one system was chosen at some point instead of another point, in a way which is consistent with the differences between the Kyoto Protocol and the Paris Agreement. And at the last few minutes, I want to mention something about the commitment period, because despite all these differences, the commitment period is the same for both agreements. You might remember actually that the Kyoto Protocol had an 8-year commitment period in the end between 2012 and 2020, but that was basically because the countries at that time, they anticipated that the Kyoto Protocol will be replaced by a larger agreement, the Paris Agreement, which they knew would be valid from 2020. So then it did not make sense to have a 5 + 3 year commitment period, and then rather had one last commitment period. But the plan was to have a 5-year commitment period also for the Kyoto Protocol. Okay, so what determines the optimal commitment period? There are many things which can determine the optimal commitment period, and we don't have a fantastic good idea of how to put all these ingredients into one single model. But let's try to use the model that we have already. And now we have a trade-off, because the optimal team in our framework will solve the following trade-off. The problem with a larger team is that over time, over time we will invest in more and more technologies. So technology, or the stock of renewable energy, will accumulate and it will increase. And this change will make it optimal for us to update. So if after 1 year we optimized over the X's again, we will select a different X than we did before. So a larger T will make basically the X inflexible, and it will make it not take into account the changes in the technologies that will actually occur over time. So that is the cost of a bigger T. It will not capture the technological progress that we will have. But there is also a problem with the smaller T. And the smaller T, I didn't talk about that, but there will basically be a hollow problem in this model. What is a hollow problem? Because I said that after the X's have been committed to for T periods, each country is solving an optimal control theory problem. That is going to take into account that at the end of this period, my value of the technology is basically going to be relatively small, because when we enter the next bargaining game, and if at that point in time I have a lot of windmills, that will influence my bargaining power in the next bargaining game in the following way. If I have a lot of windmills at that stage, you will know that even in the business as usual case, even if there is no agreement, I will not pollute that much. I will not pollute that much if I already have a lot of windmills. And therefore, in the bargaining game, you understand that I will not pollute a lot anyway. So if you calculate, for example, a Nash bargaining solution, the bargaining outcome will be that I will end up with a smaller emission quota than other countries would have, which have a smaller stock of renewable investment that has been accumulated over time. And that is basically a hollow problem. If I invest a lot in a relationship like this, that will be taken advantage of in the next bargaining game. I will take that into account, and therefore, if T is finite, when I invest over time, my investment level will basically slow down when we approach the end of this agreement. And this slowing down, or this reduction in investment level, is costly, and the reason it happens is because you benefit if I invest. You benefit if I invest, and because of that reason, it is also costly that the investments will reduce. the smaller time horizon is, the smaller the investment will be. And that it basically creates a trade-off between the two different costs. So it's difficult to calculate what's the optimal T, but what we can say is that it's not depending on the W. So if the answer is 5 years for W equal to 1, it's also 5 years for a smaller W, like as with the pleasure rebargaining game. So that should not differ between agreement according to this very simple model. But of course, as I mentioned, this does not take into account many other things, which I urge you to study in your own research. So I think I'm basically out of time. I could alternatively talk more about the literature or about extensions or robustness things that we could consider, or I can bring that up in the questions. Thanks a lot.
Bård, probably the best thing is if we just to give time for some questions, if that's okay with you. So I think Caleb, so anybody who's in the video thing can just raise their hand. So I see that there's one person, Tareen and Juliet. So let's start there, and then Caleb can also look at who else in the audience is asking questions and then pose those. So Tareen, maybe first.
That sounds great. And just a reminder, if we could keep our questions short so that we can get to everyone that we have. Thank you.
Thank you, Professor Bård, for the excellent presentation. Have learned a lot. I have two specific questions. So my first question is that the investment decision, even though you showed that it was a linear equation, so have you considered the other things that may affect the investment? Because you see that if a country wants to invest in renewable energy more, it's not, they also have to take some fiscal decisions. I mean, they cannot contribute to other sectors that can be more priority. So how actually did you incorporate all those factors in that function? Question number one. My second question is a bit specific regarding my country. I'm from Bangladesh. So in last 2021, Bangladesh actually committed to reduce carbon emission by 21%, 22%. And I was thinking that the equation you have showed us, how can it be applied for a developing country where being a very low emitters of carbon still are going forward for the pledge to reduce the carbon. So in that case, two mechanisms can work simultaneously. First of all, there should be a compensation mechanism, right, from the developing countries. So the package that they are getting from as a compensation, that can actually enhance the investment decision of the country to invest more on the renewables. So for the developing countries, when the equation do not counter any kind of compensation, in case of developing countries, both the less emission, the reward for the less emission, and also the compensation package can be incorporated. Thank you.
Okay, so maybe Bård, it's up to you. Should we collect a few questions and then you, maybe 3 questions and then you answer them? Would that make sense? Or
okay.
So I think the next person is Juliet.
Thank you. I'll try to keep this brief. I'm just wondering about the weights in the net bargaining payoff. So you assume the weights to be constant. I wonder if an extension couldn't be. Maybe it's too complicated, so I'm interested to have your take on that. If you account for the fact that countries pay attention to other countries' efforts. So if we say that the weights are a function of the other countries' efforts to reduce pollution, does it change? Can it work to adapt the model for this? Thanks.
There was one in the Q&A about what would happen if developing countries chose not to invest in renewables. How would the equilibrium change? Anything else, Caleb?
Gotta unmute myself. The top ranked, most upvoted question was around the linear model as well, which I
Oh,
think
yeah.
was touched on, and if it's with the assumptions that are made, how does the linear model fit in with the tipping points and non-linear effects, and are there examples, solutions to competitive bargaining models with something like tipping points?
So maybe Bard, let's start with those, and then if anybody else wants to kind of put your hand up or put something in the Q&A, we can build on that. But I think that's a good set to begin with.
Cool. Yeah, I think it's a great question. And I think that it's always important to think about, when you have a simple model like this leading to predictions, about how the different assumptions will influence the result and how the results will change if you have more realistic assumptions. Let me go backwards here, because the last question about the linearity and possible tipping points. So a tipping point would mean that if the greenhouse gas emissions accumulate over a particular threshold, then the cost for some countries, or maybe all countries, will jump. They can increase a lot. So that is, there are many such tipping points. For example, maybe the methane in the ground start to be released. Maybe the forest start to burn more easily. Maybe the ice melts, and then the Greenland will reflect less of the sun, or something like this. So there are many different tipping points one could consider. It's not necessarily the case that when you have many tipping points, the cost is going to be more convex, because it depends on also the cost in between those tipping points. And also, in reality, we don't know exactly where the tipping point is. So there is uncertainty about where the tipping point is. So after all, then what will be important is the expected cost for us to emit when we know that there is a certain cost, but there is also an uncertain cost because maybe we'll cross the threshold. So depending on how you model this uncertainty, for example, you could think about a uniform distribution of the uncertainty, then it can still be the case that the expected cost is linear. It will be, in fact, if there is a uniform threshold distribution. So it can still be the case that the expected cost is linear, even though you have thresholds, as long as the threshold itself is an uncertain location. But it's very simplifying assumption. I think that a more interesting answer is that if instead of a linear cost, you have a quadratic cost, then it will be the case that the more other countries emit, the less I want to emit, because the more other countries will emit, the bigger is the emission, the marginal emission cost from further emissions, and that will motivate every country, including myself, to emit less. So basically, then they will have more like a not only a crystal dilemma game like here, but they will also have a kind of a substitutability here, so that if you make an emission cut, I will be less tempted to make another emission cut. So that's in itself very interesting, and there are many papers also by myself studying this possibility. But it's a simplifying. It's most of all a simplifying assumption to rule out these possibilities in this particular model. But another thing is that the essence of what I have talked about here, this trade-off between a small and a bargaining game which leads to a small W and a bargaining game which is a big W, that trade-off will be there even in a model without any investments. So even if you have no investments, if you simplify the model without investments, then you get a similar trade-off. You will still get the case that if the number of important players in the world is larger, then it's more important to move to a system that motivates many countries to participate. So this suggests that even if countries are not investing in renewables, that you get a similar trade-off. But of course, if some countries invest, and if you have heterogeneity, so that some countries invest and some countries do not invest, it's much more complicated, especially in this coalition formation game. So then one could think that it would take more, it would be more difficult to motivate all countries to participate if they are very different, because some of them are developing countries, some of them cannot or do not want to invest, then it's more difficult. But I think that would just basically means that in order to motivate a certain, say, 195 countries to participate, the W that it would take must be even smaller than before, maybe. It's a speculation, but I think it's an interesting thing to study in future research. About Tarin's question about the K, that what if you have other investment possibilities and that you can invest in other alternative things? That's a super realistic feature that we should try to capture. The way I try to capture it in this lecture is simply by assuming that there is a cost of investing. There is a cost of investing, and the more you invest, the bigger is the marginal cost of investing because it's quadratic. That cost of investing, the idea of that cost of investing is that by investing a lot in renewable energy, you reduce your possibilities to consume or to invest in other industries. So the idea of this cost is essential to capture some of these alternatives usage that you have of your investments funds, which I think Tarin's thought about. Yeah, and let me say something about Juliette's question about the W. Yeah, the W is constant. So basically, here the idea is that if you think about the Paris Agreement and why it's different from the Kyoto Protocol, or how it is differs, one clear difference is the way in which they come up with these nationally determined contributions. So that kind of, given that choice, there is a clear difference between them, which I wanted to capture in a parameter, W. And your question is what if this W depends on what other countries are contributing? Maybe I take your weight into account to a larger extent if you are contributing more. That's interesting. And ideally, to capture this possibility, it should be something in the bargaining game itself, which allows me to kind of to take your utility into account to a larger extent if you are contributing more. Yeah, it's an interesting question. I don't have too much smart things to say about this. I think that the conditionality which is built into, for example, the Rubinstein bargaining game has some feature of this possibility, because it means that if you are offering a lot, that means that it's very important for me to succeed with this agreement, because it's very valuable for me if you're offering a lot. And because I would like to succeed, I would like to make an offer which is also sufficiently attractive so that it can be accepted. So I think that standard bargaining games is already having some kind of force in it, which captures some of this tendency that I would like to improve an offer if the existing offer on the table from you is very attractive. And it is able to capture this possibility even without playing around with the W's, I think. But it's an interesting question, which I should think more about. Yeah, maybe I'm sure that I have not given the full good answers to everyone, but I can hang on for longer if needed.
I think there's another question. Manarajan, did you have a question?
I'm not sure. Oh, yes, they're there.
Yeah. Do you have a question, Manarajan? Okay, that doesn't, maybe just the hand is up by mistake.
If not, there's a couple questions on perhaps how you would work a country like the US that and how them withdrawing from Paris Agreement or talking about that would fit into the model, and then also how maybe what your design recommendations might be for the next international climate agreement.
Yeah, so what was the first part of this question?
How the US and their recent contention with the Paris Agreement fits into the model.
Yeah, I think
on future.
Yeah, I don't know if the following will give a good answer to it, but I think that the US is an interesting case because being for an agreement to be legally binding, it means different things for different countries. Because in many countries, in Europe, for example, in Norway, even if my government, if I'm in Norway, signs a particular agreement, there is no way I can sue the government for not complying to that agreement. I cannot. It's an agreement between the government in that country and the government in different countries, and I as a citizen cannot hold that accountable. government accountable. And that limits the meaning, how meaningful it is to call something legally binding. In the US, it's different because in the US, the laws, the constitution are saying that if the federal government signs an international treaty, it becomes a national law. And that means that, for example, California can sue the government in the US for not complying with international law. And that means that for something to be legally binding is more severe for the US government than for many other countries. And that is one reason why the US insisted that emission cuts and the Paris Agreement should not be legally binding, because it's a bigger cost or possible cost for them than for many other countries. And about moving from here, I think that many of these designs are facing a trade-off between having an agreement that is appealing for many countries, so that many will like to participate, at the same time as it's demanding, so that emission cuts will be meaningful. That is such a trade-off. I think that when you think about this trade-off, these two decisions, participating or cutting, have different, are not equally reversible. So I think that one of them is more long-term than the other. Of course, it's possible to participate and opt out. Canada did that in the Kyoto Protocol. But nevertheless, it's much easier to increase or decrease a particular contribution or emission cut. So one way of taking advantage of this asymmetry is to make sure that now we have an agreement where everyone is in, as in the Paris Agreement. And once you succeed by having such a large coalition, then it might be possible to gradually move towards a more ambitious system with a larger W, if you want, so that the emission cuts will be larger, but only at such a speed that countries will not try to start to leave the coalition. I think that might be the better way forward. So to lock in as much as you can, everyone, maybe include other carrots like trade agreements and so on, and then try to make an agreement more ambitious as we go forward.
Okay, brilliant. I think there's one final question which is about CBAM. So how is CBAM gonna how do you think CBAM will affect the sort of international agreements? Is that something, just any comments on that?
No, can you elaborate?
So basically the question is thinking about the carbon border adjustment mechanism that the EU is introducing.
Yeah.
And how that would that be kind of a replacement or something that could work better than the kind of COP type things?
Good. Yeah. I think I referred to that just before this question came up when I talked about other possible carrots, because I think that it's very difficult to motivate countries to comply to international law, and as long as I think that it might be necessary to find all the carrots or sticks that one can find, and clearly trade policy is one such thing. That if you can use trade policy in a way which is not used only for protective means, but in a way so that you can motivate countries to participate and comply and cut emissions, and discourage them from not doing that, that can be valuable. And I think that Europe's carbon border measure, CBAM, is one such possibility. I think many times it will here be the details might matter a lot, to the extent to which this is going to be only punishing or also allowing the exporters to improve or to reduce the tariff if they can reduce emissions. So I think that the main details that we could continue to discuss, but it's an interesting topic to this investigate this.
Brilliant. Well, thank you very much, Bård. I think we've reached the end of our time, but thanks a lot, Bård, and thank you all for coming, and look forward to seeing you next week. Thank you.
Thank you so much.
Thanks very much, everyone.
Bye.
Thank you very much.
Thank you.